Hey, we're going to look at part 5 for gas stoichiometry. We're going to be going back to looking at the ideal gas law. So if there's other information provided for the chemicals in the reaction when we're looking at gases, so for example, they've provided you with a mass, we're going to look at the ideal gas law to perform calculations. And so as a refresher, ideal gas law is the pressure times the volume is equal to the number of moles times the constant multiplied by the temperature. So V is going to be volume in liters. T is going to be temperature in kelvins. P is going to be equal to pressure in kPa. And N is the number of moles. And R is the universal gas constant. And it's 8.314 kPa times liters over moles times temperature. Okay. Other key pieces that we need to remember. We need to remember SATP, standard ambient temperature and pressure, is 298.15 Kelvin or 25 degrees Celsius and 100 kPa. And if we wanted to remember what STP was, it is 0 degrees Celsius and 101.325 kPa. So those are some big pieces of information that we need to remember. PV equals nRT. Here's going to be where we get our moles from. And SATP. And we also need to remember that there's values that go for this. When we look at SATP, we remember from gases that the molar volume is 24.8 liters per mole, and that the molar volume for SATP is 22.4. Okay, so those are key pieces that we need in order to do gas stoichiometry. Let's look at an example. If 300 grams of propane burns in a gas barbecue, what volume of oxygen at SATP is required for the reaction? So let's write out the reaction first. Propane, you needed to remember, is C3H8. There are places in the data booklet that you can look. I'm going to let you hunt for that. This is a combustion reaction. So we're always going to get carbon dioxide and water as a vapor. First rule of thumb when we balance is we balance the carbons first. We balance the hydrogen second. And then we balance the oxygens. And here we have 6 oxygens, and here we have 4 for a total of 10. And so I'm going to put a 5 here. Always, always, never fails. Carbon first, then hydrogen, then oxygen. The next piece that we're going to do is we're going to write down our known information. We have 300 grams of propane, and it's asking us for what volume of oxygen are we going to have. So it tells us at SATP. At SATP means that it's going to be 25 degrees Celsius and 100 kPa. So temperature is equal to 298.15 Kelvin. Pressure is going to be equal to and then we need to be able to always get down to moles. So this part we will have to determine. And then we can look at this. So when we do this linearly, we can start with our 300 grams of C3H8. And I know that the molar mass for propane is 44.11 grams per mole. Now I can look at mole ratio for oxygen, and I have 1 mole of propane for every 5 moles of O2. Now that I'm in moles of O2, this is where it's a good place to stop. So 300 grams multiplied by 1 divided by 44.11 gives us 6.80 moles of propane. When I multiply 6.80 moles of propane by 5, I get 34.0 moles of oxygen. Now that I have moles of oxygen, I can go down into the PV equals nRT formula, and I can isolate my volume out this way. Okay. And so I will then find out that my volume is 843 liters of oxygen. That's how much is required. The reason I don't try and do, you absolutely can, but why I stop at this point and I move into this formula is because there's too many pieces of this formula that you would have to be conscious of when looking at units, that it's easier to just do linearly until you get to your moles of oxygen and then move into this formula. If you want to challenge yourself and do it linearly, you can, but I've seen more mistakes by trying to do it linearly than I have when you stop it. So here's grams. Here is propane. There's the moles, and you're left with moles of O2 when we do unit analysis. So you're going to stop here and you're going to work on pages 14 to 16.